Okay, hello everyone. Welcome to my talk that's called From Words to Wisdom. Maybe a few words in private about me. My name is Marcin. I'm working as an architect at Ratec in Germany. I have an 8-year-old daughter that I'm taking care of, which is consuming a lot of my time beyond work. And then I'm a large fan of Warhammer 40k, hence some theme on the slides. And I'm doing triathlon in my spare time. That's where I can. Okay. Let me maybe begin with some brief history of search. How did search develop over the years? It started so in the beginning when we were using dial-ups. Maybe someone remembers in the hall using modem and all the beeps, and there were just a few search engines out there. Like WWL Wanderer was the first one written in Perl, and then like Yahoo and AltaVista were like the bigger names you could probably recognize. Then search was about comparing strings. It worked well because there was not that much of a content to compare, and usually you had to browse to find something you were actually looking for, rather than find something within a mess of results that you were getting. Then Google came and invented an algorithm called PageRank, and it was working well for about a decade. It was about weighted sources. So when we had some source, and there were other sources pointing at it, the more sources were pointing at it, the higher it was ranked, and also the weight of the sources that were pointing at it were taken into considerations. Then it was a bit abused by different SEO algorithms when people were producing some blogs and writing something just to make the results appear higher in the lists. Then a decade later, like 2012, Google came with a white paper called Things, Not Strings. It was about the concept finding the right thing, and then starting building similarity and all the results around it. Basically, what Google did was building a knowledge graph, and they put their data into a knowledge graph, and you could explore around it. So the smart search began. Now we are in the era of AI, when Google and other search engines extend your search by generative output, and they basically build a RAG around it. So you can get, I think most of the web search engines will bring you like an AI overview for your query, whether it's DuckDuckGo or Google, where you can find the summarized information. And this leads us to my presentation, where I will try to introduce you to a RAG and how to use LLMs. They tend to have this feature called hallucination, and it's where when they don't know what your answer, they will make things up, and they are very good at making things up. It is because they are trained on a specific data set. Usually it's not very up to date, and if you're using like some private data, they also not know about it. So you have to feed them the information. They can then analyze it and return you your query results. Okay, and to understand that, I will give you a brief introduction on what are vectors, and then about text embedding, so changing text into vectors. I'll also explain a little bit on vector databases, and at the end of the talk, on this talk, we'll build a small RAG using LangChain4j. Okay, then this is a vector. It's a numeric representation of basically any object. It could be an image, and it could be in text. But the easiest ways to solve it is like a two-dimensional section. It has its parameters, where they are the difference between the end of beginning of vector And since it's numeric, you can do some math around it. So, for example, we can add vectors. Adding A to B would result in having a new vector C, and then you can reverse it and subtract it. You can multiply vectors, having a dot product. And with that, with having a dot product, we can count a similarity of a vector. So we can compare two vectors and see how similar they are. There are more functions to that. One of them would be cosine similarity. It calculates the angle between the two vectors, and it goes from -1 to 1, meaning 1 is like the vectors are the same. -1 would be the opposite of it. We can also calculate the distance between two vectors. It goes then from 0 to infinity, and here reversed, it will be when the distance is close to 0, it would mean that the vectors are very close or are the same. Then we can imagine ourselves like easy vectors that have 2 or 3 dimensions, but the vectors that we use in the RAG will have many more dimensions. It will be like 1,000 or 8,000, depending on the embedding model we are using. And going over to embedding, it's the transformation of our input object into a vector. And how do the LLMs do it? They work basing on tokens. Tokens are some characters that are glued together, and they usually sum up to like a quarter of a third, 3/3 of a word, or 3-4 characters. And what the LLMs models are good at, they understand the relations between the tokens, and they can produce you output basing on these statistical relations. So having that said, embedding, we now know that the embeddings are vectors, and they are a numeric representation of our input. By knowing that, we know that the vectors that are mathematically similar or close to each other, their semantic meaning will also be close. So we can now compare our vectors and find information that's close to our input. The embedding models, they do transformation for us. And what is the characteristic of that transformation is that for the same input, you'll get the same result. So it's not random, as long as the input is the same. But if you put a different input, the output result will be different. But it will be similar if the both inputs more or less talk about the same thing. And how do these models know that we are talking about the same thing? It's because we have words that have a meaning in a context, and the models work with attention or self-attention, where they can find they can understand and they can catch the context of our input by comparing the tokens within the sentence, and they will build, or they will highlight the most important areas, and that's how the context will be caught. So we have an outgoing vector of our embedding, of our text, and there are many parameters. We don't know exactly what are the values we know the values behind the parameters, but we do not know what do they actually mean. But what we know is that the parameters have a specific meaning. So having like a very simple example, where we have a 4-dimensional vector, and we have like a parameter for living being, a human, or living at home, or feline, and we would embed cat, human, and tiger, then we would see that cat and tiger, they are very close at the feline dimension of it, because they are both cats, right? But then like cat would probably be is like more a thing that's living at home. So it might be similar in that area to a human, but it will differ from a tiger that usually lives in the wild, unless it was a domestic tiger, like the one on the picture. Sadly, it's that, but we all know it from Hangover movie. Okay, then when we have embeddings, and basing on this example from it's what OpenAI did, and they produced a sample out of 5 categories in DPpedia set. They took the 100 results of each category and they embedded it. And then they transform it to 3 dimensions, so we can see the feature that that the embeddings that were made of the same category would then gather in the space more or less in the same area. So like animal descriptions or athlete descriptions or theme reviews, they would all gather together in a certain space. So if you look, if we will then pick things out of that space, they will more or less they will touch the same area. Now we have many embedding models, but everything started in 2013 with Word2Vec. It was the first embedding model, but it did not have the attention mechanism. It was vectorizing sequential words, and you could compare vectors back then, but you had no context. The context showed up first in 2018 with introduction of BERT, again by Google. And this is when it came into the area of having a context relative, where context search became possible. The feature of, since we have the vectors, and another feature is that the distances between vectors will have some meaning. So imagine like we have embedding of Poland and Warsaw, which is the capital of Poland. So the distance between Poland and Warsaw of the vector will be the same like between Thailand and Bangkok, because it's more or less it will be the meaning of a capital. So if you add a vector of a capital to Poland, you will end up somewhere in Warsaw. And the distance between Warsaw and Bangkok will be similar to between Poland and Thailand. So that would be the beginning, the theory. And there are some tools that are worth mentioning when you want to get into LLMs. One would be Hugging Face. And if you think of Hugging Face, you can compare it to a repository of model. So it is a repository of the model, so we can compare it to NPM or Maven Central, where you can find many models and documentations. Then you can actually read how are they trained, what are they good at. And then you can, another useful tool will be Ollama. Ollama is can be compared to Docker, and it's a runtime where you can run your models locally on your own machine. What's worth mentioning is that you can run many models on a laptop, because what is consuming most of the resources is training of a model, and while having it run will consume less power. So you can run relatively small models locally for some test purposes, but the bigger ones you will need to run in a computing cloud. The another part of a puzzle to build a RAG is a database, and there are different databases for different purposes. So we know relation databases where data is stored in rows and columns, and you can search by comparing the data. We have document databases where you can store documents with a payload, and they are convenient if you want to store, I don't know, some product information. And then recently we have came up with a new type of databases, are vector databases, and they are quite similar to a document database. So they store you the keys, they store you the payload, but they also store the dimensions of your vectors. And it is important when you embed your text and you put it in the database that you store both the embedding and the original payload, because it will be then hard to find out what actually you embedded if you just have a vector, and you need the original text for it. And one more thing maybe about embedding is so embedding models are like a pure function, but they can be, and they will produce you always the same output for the same input. But in theory, it can be reverse engineered. So if you know which model was used to create the embeddings, you can try to reverse engineer the original input. So we don't want to embed unencrypted sensible data because it can be hacked, or it can be then traced and reversed. It's not safe. The vector databases, they offer you to search by the vectors, and it works. We pick, when we create our schema, we pick the distance functions we want to use. And we also, when we create a schema, we define how many dimensions do we want to store. You can only do search for the same amount of dimensions. So if you have to use the same embedding model for creating your data set, and you use then the same embedding model to transfer your queries into a vector, the database will then take the vector and it will do a search results. It will find you the closest results and return them to you. For example, you want to find results that are, in this example, at least, I don't know, higher than 0.7 distance. Okay. Like I said before, when we prepare our data, we must use the same embedding model for the data and query, because otherwise you will not, the search will not bring you the result you're expecting. Because even if you use the same amount, well, we need to use the same dimension count, so it needs to be the same. You have to use the exact dimensions as you define the vectors store. But if you use a different model, then the query vector will like carry another information in these dimensions that actually the data is storing. So the results you are getting will be relevant. When it comes to choosing the matching function, Oracle claims you should use ideally the same distance function that was used during training of the model. But then if you look at OpenAI docs, they say it doesn't matter that much which distance function is used, and you could just go with constant similarity for most of your cases. So if you are thinking which one to pick, just start with Kotlin and see what are the results that you get, and if it's not satisfying, you can experiment with others. When we compare different databases that are on the market, there are now products that specialize themselves in storing vectors. It will be Kudron, Pinecone, and Malthus. They offer more or less the same functionality, but also the big names, they also bring the vector search to their databases. So you can take Elasticsearch and have a vector in this. Neo4j lets you build graphs, and they also have a vector index that will let you to search by vectors. Redis is also there with vector search, and I think Postgres as well. So we can depending on what data and what are you having, where is your actual data located, you can probably extend your engine by vector search. Then the process of building a RAG is like the RAG process consists of 4 steps. The first one will be indexing, where you digest your data and put it into a database. And then you retrieve it, so you do the search. You search for the data, you augment it, so you generate the output. So you do a query based on your search results. When you prepare your data, you have some input documents, and the first step will be to pick your embedding model. to transform your data into vectors. And there are then different strategies how we can approach it. So if you have like very large documents, you may want to have them split. So you create segments out of the documents. You can decide whether you want to segment, I don't know, by pages, by paragraphs, or by the amount of words or tokens. And when you create these segments, it would be important to have a layout. So also that you have you define an overlap. You define an overlap of these segments. It is because when you will do this, when you're doing search, and the information you're looking for is somehow split between the two of the segments, you would like to catch the whole context. That's why you do the overlap. It can be like a 10% of your segment size, and it will improve your search quality results. Then is the next step will be querying. So you have your query. You throw it through to your chosen embedding model, and you perform the search, and it will bring you the similar segments. What's noteworthy, maybe again around embedding, is you use embedding models for text. But if your data is in images, you would then pick a model that will transcript your images into text, and then you can have the text embedded, for example. Okay, so now we have our fragments that carry the information. You would then take again our query, the input documents where the input data that we expect to find our answers, and we'll put into LLM, and it will then give us an answer basing on provided information. This will lead then to the fact that it should not hallucinate, because the model is actually very good at finding information in the text that's provided, and it will also know what are you asking it if it's a private data, right? And the model you choose for LLM in our case is Claude Sonnet 3.7, which is a reasoning model. That's how the demo is built around it. Then I'm using LangChain4j, which is Java implementation of, well, it's inspired by LangChain, and it's Java implementation. So if you're not good at Python, you can start developing Java. And it became the final version 1.0 just yesterday, which is worth nothing. Not all of the modules are there yet. Some modules you need to pick a beta versions or release candidate. But the major core is now released as a version 1.0. Then a mixed by is chosen as embedding model, and it has 1024 dimensions. Okay, everything is packed in Micronaut. If you are still using Spring, then maybe it's worth considering switching to other frameworks that are faster, like Quarkus or Micronaut, with ahead of time compilation. So how it works? We will have a data set that we put into the database using document parsers. We will split the text into segments and store it in the vector store. And then there is an PI build that will let us query on the related information. So let's maybe go to the demo part. I just need to find. Oops. Wrong. Where's my mouse? Okay. Okay, so this is Solana. It looks more or less like, okay, so you can list the models you have, you can pull models, you can see what models are running. So we can, okay, so Llama is already running on my machine. And then let us maybe take a look at the code we have here. Okay, it should be visible. It is. Okay, so what we have here is we will start with a document reader. There are two documents that are indexing. We will play with a fluff Bible of Warhammer 40k. It's around 400 pages explaining us the Warhammer what are the fractions there, some history, and things around that. And the other document that we'll be indexing is the latest game rules, which are in this PDF. So I'm indexing the text content. I'm not embedding images here. And this explains us the rules and that we use to play the game. Okay, so we should start by creating let's maybe see if there are any questions, and maybe you can answer them. Where are the questions? They should be here, right? Uh, 11. Okay, there they are. To pick up the duck. No, I did not. It's mine? No, I'm room 12. Yeah, this one. So there are no questions. Great. Okay. Okay, so let us go back to, so this could run to AI UI. I have already defined some collections here. I do have a collection where I split the text into bigger chunks and also to smaller chunks, because I will show you the difference of using a large model with 200 billion parameters, and also I will show you how we'll perform a small model that I can run locally, and you'll notice a significant difference between how they can handle the input. Okay, so let us create a new collection. We'll name it GeeCON Live. It needs to be 1024 dimensions, and we'll use Kotlin function for distance matching. Okay, and I will run not this one. I will run the documents reader in background, so it will no, not like this. Luckily it's maybe to start micron out. Because the application is running, so I need to stop it. And we'll change the collection to live. And now we can start digesting. And let me go back to the code and explain you what's actually happening here. So LangChain4j will give you tools to index your documents. So you can read, so we can get a document reader, and you choose which parser you want to use. In my case, we'll read PDF documents, but you can, there are text readers, or you can write your own parser that will read the data. It will then create 2 documents for us that we will split. We can split it into the given not found. GeeCON Live does not exist. Okay. Right. Let's just copy it over, and it will be better. And we go again to the application now, and yeah, and we fix it. And now it should run. Document reader, and let us run it. Okay, so it now works. It read out around 300 segments, and it will store it to the database. What's happening here? Let us browse a little bit through the code. So we have so we read the documents and we want to send them to our vector store. So we have an embedding model. That's a class that connects to Llama in this case, because we use a local embedding model in our case. We pick what's the model name, and we tell us where it's located. In my case, it's running locally, and it then lets us to embed the input and store it in the vector store together with the original text and some metadata around it. And the metadata, it will help us to it can be like some tags, like what documents did we index, or what's some text around it. We can then use it to push it into the query if we want. We can read the metadata during the embedding process or the query process. Okay, then that's what's happening here. And the next thing is we want to once we have pushed the data into the vector store, we have our agent built around it. So we have the question service that implements a chat function. To build it, so we have an AI service, and we bring a chat model into it. The chat model, I have defined two chat models. One is the local one, like using Llama, and the other one I use OpenAI chat model, where I will connect to Cloud Sonnet. It's running on AWS in my case. So I give my private AP key. I define the URL where it's running. I give the it's actually given here twice. I give the name of the model. I do enable some logging, so we can look into the logs and see what's actually happening with the queries. And there is this temperature parameter. It's used as it goes between 0 and 1, and at 0 the models will be less creative in analysis. So if we want them just to bring us pure results, or to be less verbose on what they find, we tune it down, and when we want them to be more, I don't know, talkative, we should put it up, depending on what kind of agent we want to build. So we can play with it and see how it affects our query results. Llama chat model is basically the same parameters. It has a different temperature. You can also set it to 0. And we will switch between two of them. First, we'll start with the OpenAI model. So this is what we give as a chat model. Then we need to define where is our data coming from. So we have a content retriever, which will connect to our embedding store. There are ready connectors, so we are using a Kudrant. So I'm using a Kudrant embedding store here, which will connect to the database. And I give it the embedding model, which I use to embed my data. I also say what is the minimum score, what's the minimum distance I want to find. So it's like I want my query results to be better than 0.6, and I was just 5, and I want just 5 best hits. Then it also lets you to build a memory around it. So because LLMs are stateless, and if you want them to catch up with the context, you should always pass it over your chat conversations. Here we have then done it for us. We will always transmit the 10 latest messages within the query. And there are also system messages you can use. System messages always pass as the first message to LLM over and over again with each query. And you can define some behaviors. So an example, I want to pretend that my agent is is like a librarian, and it will refer to me as a lord, and will use like medieval style English. And I also instruct it to process an answer and limit itself to around 100 rows, so it will not produce large walls of text. Okay, so let's see how it works. And we'll ask it a question based on game rules. Okay, it ended here. Start the app, startup completed, and it should tell us that it's around it's actually 2 inches between models in a unit. And it will explain us that they need to remain the coherency between through the entire game. And when we look into the logs, we then see we are passing the system message and our query, and then we are also pumping in the information we want to the model to use for the answer. So it's actually extracted out of our input data set, right? So it found relative parts of the game rules, and will give it to the model, and then it gives us the answer. And then we can try and ask it whether there are some specific rules for vehicles in this context, right? So is it an it will think a bit, and it will the answer should be that it's the same. So the vehicles, they follow the same coherency units as exact models. We did not ask the model for it, but because we are using the chat memory, we are passing over the conversation to the model, and it then can analyze it and find out that actually we are giving this question within this particular context. We can also ask it for something out of the game universe, and we can look who betrayed. Let's check who betrayed the emperor. Emperor is like a god living on a golden throne because he's almost dead. And let us check who betrayed him. And it shall say us it's Horus. Let's wait a bit. Right, during the dark days, it was the Horus that betrayed the emperor. So it's like information that the model does not have. It's taking it out of the context. And now let us switch to the local model and see how it will behave with the large because it will be running locally, so it cannot handle that much of a context window, like the reasoning model I'm having here, because basically for this one, you can throw out large documents or large sources, and it will perform very well with finding you the answers. But if you want to keep your costs low, for example, you will use a smaller model and maybe run it on your machines, and you can also build a system around it. But you need to be aware that the quality and the input needs to be different than for a large reasoning model. So let us stop our app and go over to the Olama model here. So we'll switch like this. So now we'll be using a model that's defined locally, and it's Llama 3.2. It's quite small model. So if we look, I think it's 3 billion parameters compared to Cloud Sonnet, that's around 200 billions. So it's I guess it's around 60 times smaller. the parameters, the size of the models tells you how many parameters has how many weights. So how many weights are in the model. The bigger the model is, it has the more parameters. It's also bigger, and it consumes more resources to run. And the model we'll use now is the Llama latest, which is running locally, and the whole model is just 2 gigabytes. Okay, I did start it. Now let us ask it the same question about coherency. Okay, and now we can see that it somehow lost itself. In terms, it did produce us a lot of text, actually not replying to the question, because the context windows is a bit too high for him to find out. It even lost the instruction that it should limit itself to 100 words, and it also lost the instruction that it should refer to us as my lord, right? And we don't see then the answer here. But what we can do, we can use the same model, but with a different data set, or the same data set but structured differently. So we will take the other collections, the other collection I have. That's called GeeCON small. And what I did here is I have the exact input data, but split into smaller chunks. So the first one was about 5,000 characters each, and the other one is 5 times smaller. It's just 1,000. And so there are more vectors stored in the database, but the information is, but we should deliver then more precise input. Okay, so I think I did start it, right? Oh, I did not. No, it's not running. Okay, now it's. Oh yeah, now it's running. Okay. Sorry. Yeah, I did stop it for a reason, to change the embedding. So to change the source. Okay, we use GeeCON small. We will start it. And we will ask again the same question. And this time it should give us the answer. Right, it's there. Because the model is smaller, I can run it locally, and it will still bring me good results as long as I do prepare the data correctly for him. So we'll see that we are still passing the information here. So we did find relevant information. It's in smaller chunks, and because we provide less data, it performs quite well, and it brings us the results. Okay, so this will be the introduction into how to build a Rex. So you can see it's quite easy. You don't need to know Python to start playing with. So we all Java developers and Kotlin developers can now build our own Rex. And we don't need AI to brew out the Python code for us, which you can also do. But the entry is now less, so the learning curve will be now smaller to build Rex with Java. Okay, so let us see if there are any questions. Well, there are no questions. Or there maybe are no questions. Sorry. There are questions. Okay, maybe you can read them, because for some reasons I don't know how to switch them here. If we generate vectors for an event in different countries, will the vectors differ only in specific dimensions? It's hard to answer. Like, as I understand it, like if we describe some events happening in a different country, I don't know, like some kind of news, right? Is this what the question is about? I cannot tell you exactly which dimensions will differ, but as long as, but if the characteristic of the vectors is that if they touch the same problem, they will somehow gather in the same space. The distances between the parameters that are responsive for some features of the input text, they will be close. Yes, they will probably not be the same, but they will be close. So if you describe, for example, give a description of a president of India and the king of Thailand and the president of Poland, then the output embedding will be similar in the areas of the vector that are responsive for example, for a ruling person. They will be close there. And if you then do a query, like tell me about the world leaders, it should then you find the text in the dimensions, because you are asking for the world leaders. It will then search you the data that's telling about world leaders, and you should find it. I hope that answers your questions. Is there another question? Okay. So thank you, everyone. I hope you enjoyed GeeCON. We have many wonderful talks here and a good party. So see you again maybe next year. Thank you. I'm on my LinkedIn, and the code is also at my GitHub repo. You can use and play with it if you want. And that's it. Thanks.